So this is the second video about volumetric analysis for Advanced Higher Chemistry Unit 3. What we're going to be talking about are a few different types of titration. There will be another video after this talking about the final type of titration. We're going to focus on 3 in this video. So the first type of titration is an acid-base or an acid-alkali titration. These are the types of titrations that you know from National 5 and you've been doing over and over and over again. And so we're not going to go into too much detail about how to do them. The most important things to remember are, now that you are doing Advanced Higher, you could be asked to choose an appropriate indicator. Now remember, those are found on page 14 of the data booklet. And if you know what pH your salt is going to be, that's what's forming at the end point, or if you're told or shown where the end point is in terms of the pH scale, choose an indicator that will not change colour until the end point, and will definitely change colour in the middle of that end point. The other thing to remember is that if you are explaining how to do an acid-base titration, whichever solution is your standard, whether it's a primary or a secondary standard, that is what goes in the burette, and the unknown solution is what goes in the conical flask. The second type of titration is known as a redox titration. Now, while that term has probably never been explained to you or used, you did look at lots of redox titrations as part of your preparation for higher, and many of the example questions in past papers and in your final exam would have used redox titrations. What a redox titration is any titration where instead of it being an acid reacting with an alkali, you're reacting an oxidizing agent with a reducing agent. And the most common ones are things like potassium permanganate or dichromate, which are self-indicating. So permanganate goes from purple to colourless, and dichromate would go from orange to green. Another common redox titration would use iodine, and the indicator for that would be starch, because where iodine is present, it will look blue-black, and then depending on what else is in solution, it'll either turn colourless or it will turn yellow when there's no more iodine present. Now, redox titrations are done exactly the same as your normal acid-base titrations, and what tends to happen, however, is that they are done at much lower concentrations than your standard acid and alkali. So you might need to get used to using scientific notation. The final type of titration, and the one that we're going to spend a lot of time going through a couple of examples for, are complex symmetric titrations, which you can probably tell from the name are dealing with transition metal complexes. Now, these titrations involve ligands being titrated against transition metals, and there are 2 ways in which these titrations can be used. The first one would be to determine the stoichiometry, or the mole ratio of metal to ligand in a complex, so that you can then put together what the complex looks like. The second type is a more traditional type of titration, where you're using it to determine the concentration of transition metal in an unknown sample using the ligands and using the molar ratio. So the first type, determining stoichiometry, we'll go through how that is done. So this type of experiment is interesting because both solutions, the ligand solution and the metal solution, need to be standard. You need to know their exact concentration. So the transition metal ion solution has to be a standard solution, and the ligand solution has to be a standard. These can either be primary or secondary standards. The reason for this is if we want to work out how many moles of ligand are reacting with how many moles of transition metal, we need to know exactly what the concentrations of those solutions are so that we know exactly what the mole values are for each solution, and then can work out the mole ratio. Normally, you know the mole ratio and you know one standard solution and you're using that to work out the other concentration. This one, you know both concentrations and you're using the volumes to work out the mole ratio. So the procedure, your metal solution typically is what goes in the conical flask. And standard ligand solution is what goes into the burette. You will have an indicator. Now the indicator needs to be something that will change colour when all of the metal in the conical flask has been used up, has been bound to all of the ligand. Or it can be another metal that when you have excess ligand, as soon as there's one extra drop of ligand, that metal will form a complex that turns colour. You don't really need to worry about the indicators for this, just that they are used. Now from the titer of how much ligand solution you needed to use, you can work out the mole ratio of ligand to metal within a complex. So here's how we could interpret some results. So we were told we've used 20 centimeters cubed of 0.02 mole per litre copper chloride solution, and it was titrated against a 0.1 mole per litre ammonia solution. So we have two concentrations that are standard. We obtain the following results. So when we do it, we look at the results that are concordant. Those are experiments 2 and 3, and we work out that the average titer, the average volume of ammonia solution, was 24.05. Then what we can do with this information is work out the moles of copper and the moles of ammonia so that we can work out how many ammonia molecules are being bonded to the copper. So we're using our N equals CV for each one. For copper, remember we're turning our volumes into litres, so the concentration is 0.02, the volume is also 0.02, so we get 0.0004, or 4 times 10 to the minus 4. When we do the same for the ammonia solution, using our average titer, we see that the concentration is 0.0024. Now, just like we've done in gravimetric analysis, when we were working out the number of moles of water, moles of water of crystallization, when we've got a ratio, what we do is we divide each number by the smallest number. And so we're dividing by the moles of copper, and we get a ratio of 1 to 6. That means we know that 6 ammonia molecules are bonding to each copper. That means that we can say that because ammonia is a monodentate ligand, it only forms one bond, the coordination number of copper is 6. It also means that we could write down the complex and name it. So that complex is missing a 6, so it should be CuNH3 6 2+. And we know that it's going to be 2+ charge because the copper started off as 2+, and ammonia is neutral. If we were to name it, remember ligands go before the metal, and there's 6 ammonia, so it's hexaamine copper 2. Copper 2 because it is a positive complex, so we do not change the name of the metal. Our second example of complex symmetric titrations are working out the metal concentration. And this experiment that we're explaining is one that we would like you to have tried in class. But if not, this is a sort of rough guide to using complex symmetric determination of nickel using EDTA. So nickel can form a hexadentate complex with EDTA. So the EDTA completely surrounds it, and it means they react in a 1-to-1 ratio. So when we do a titration, however many moles of EDTA have been used tells us exactly how many moles of nickel were in solution. By using a titration, the concentration and mass of nickel in a sample can be worked out. So we'll initially work out concentration, and then using GFM we can work out mass. So the procedure, we need to know some background information on this reaction in particular. So we are going to weigh out an accurate approximate sample of nickel and make it up to 250 centimeters cubed. From that 250 centimeters cubed solution, we will take portions and we will use a standard solution of EDTA to titrate it. So as I said, 25 centimeters cubed portions of that nickel solution to do the titrations. We will use an indicator which is called murexide indicator, and we also need to have some ammonia present to make the end point clear. And I'll explain more about that, I think, on the next slide. We can then do our titration, work out the number of moles of nickel in the 25 centimeter cubed portion, and therefore the number of moles in the 250 ml flask that we started with. And from the number of moles, we can work out the mass of nickel and the percentage of nickel in our starting compound. So the details that I'm going through, so this is going to be a worked example. We weighed out 2.626 grams of nickel sulfate hexahydrate. And it was dissolved in water, made up to a 250 ml solution in a volumetric flask, following our standard procedure. And so from this 250 ml or 250 centimeter cubed solution, we were using 25 centimeter cube portions, or aliquots as they're sometimes known, to do each titration. Now the indicator or indicators for this reaction. EDTA has 4 carboxylic acid groups on it, and it will only fully bond if all of the acid groups are deprotonated. So we know a carboxylic acid has the COOH group on it. In order for EDTA to fully bind, we want to turn all of those COOH groups into COO negatively charged groups by removing the protons. To do that, we need to add a base that will accept those protons or steal those protons away from EDTA. And ammonia is used for this. So it's creating basic conditions so that our EDTA is absolutely ready to do its complex forming. Now, also we have an indicator called murexide. Now, murexide will bond to nickel, but EDTA will bond better. So during this titration, the EDTA bonds to the nickel, and the murexide is then left on its own. And when the murexide is no longer bonded to any nickel, it will change colour. So it starts off a yellow-green colour, and then it will end up a violet colour. So as soon as that murexide indicator is on its own, it will turn violet. It'll start yellow and it'll go violet. So we're looking for a purple colour as our endpoint. Now, we made a 0.1 mole solution of EDTA to titrate against these 25 ml portions. We did 3 experiments. We take our average of our concordant results, which are experiments 2 and 3. That first experiment is a rough titration, and we get an average titer of 9.85 centimeters cubed. We can now do our calculations. So we can, how do we use this to calculate our mass of nickel? Well, the first thing we need to do is work out our moles of nickel from a titration as we normally do, remembering that nickel and EDTA react in a 1-to-1 ratio. So our moles of EDTA, we know our titer is 9.85 centimeters cubed, so that is 0.00985 litres. Our concentration was 0.1, so that gives us 0.00099 moles, and you probably would be able to round that up to 0.001 moles if you wanted to. The ratio is 1-to-1, so the number of moles of EDTA equals the number of moles of nickel. Now that we need to really specify was the number of moles of nickel in the 25 centimeters cubed portions we were using. We made up the nickel in 250 centimeters cubed. So in the flask, there would have been 10 times the number of nickel moles. So we multiply it by 10, which gets us 0.01 or 0099, depending on how much rounding you would like to do. So we know our moles in our nickel sample. We can then turn that into a mass using the gram formula mass. So nickel weighs 58.7 grams, that's its relative atomic mass. When we multiply, we get 0.581 grams of nickel in our sample. Now this could be used, you could be asked to then work out a percentage as your final thing. So if that was our mass, remember from a few slides back, we used a sample of 2.626 grams. To do our percentage, we could we use our mass of nickel divided by our mass of sample multiplied by 100, which is 22.1%. Also from this, if we wanted to, if we know the mass of nickel, we could work out also whether or not there were 6 waters per molecule as we expected, or whether it was different. So we could use that as a different way of working out the waters of crystallization as well. So this was an introduction specifically to complex symmetric titrations with a specific example on how to work out the mole ratio within a complex, and then how to do this nickel titration using the Rexide indicator and EDTA. But we also touched upon acid and base titrations and redox titrations. There's one more type of titration known as a back titration, which will be the topic in our last video on volumetric analysis.